Welcome back, Night Owls. This is Dr. Nighttime, and tonight we're doing something a little bit different. Um, Here, what I'm going to do is I'm going to run through a practice online exam P, or the sample exam P that the Society of Actuaries provides. Going through showing a lot of the shortcuts that I'm going to use, not really going into such detail about them, and if you have any questions about what sort of trickery I'm using, feel free to ask them in the comments, and hopefully by the end of that business day, I'll get back to you on that. I will mention going in that on this exam, most of the questions are not going to be textbook cases of use this property of this distribution to find this one thing, right? There's always something weird about it, or pretty consistently something weird about it. So that you have to combine your knowledge of probability with some basic problem solving skills that hopefully your instructors have been helping you build. Although, with the actuarial students I've worked with, I feel like this is underemphasized in most actuarial science curricula. Anyway, let's hop to it. As soon as it loads. Oh, here to click next. Okay, I was wondering where did I go? All right, two fair dice, one red and one blue are rolled. Let A be the event that the number rolled. Okay, that one's odd and the sum is odd. Okay, it's that independence thing, right? Obviously, A and B are independent, A and C are independent, B and C are independent, but if A and B are both true, then C must be false, right? So they're not mutually independent. They're pairwise independent, but not mutually independent. Okay. An auto insurance company has 10,000 policyholders. Each is classified as young or old, male or female, married or single. Of these policyholders, okay, and they're giving these young, okay, and saying how many are young, female, and single. All right. Venn diagram, draw a circle, Venn diagram. Let's say young, married, female. It's saying 600 are young married males. Young married male, 600 here. Young married is 1,400, so that puts 800 here. 3,010 married males. Married, but not, yeah, so in this circle, but not in this one. It's going to be here. We have the 600 there. 2410. They said 1320 young males, so outside of this. Sorry, I put this in the wrong place. This is the 2410. Outside of this, inside of this, they said 1320. Yeah, so 720 here. Not sure why that's popping up right now. Okay, it said 3,000 are young. Okay, 14, 2120. That leaves 880. You know, maybe I should have, instead of Venn diagramming this, should have done the, well, I feel like this is a little more flexible. 4,600 are male. 14 plus 2410 is going to be 3810. Wait, sorry, I want everyone outside of this. Outside of female. 2410, 3010, 3730. It's going to put 870 out here. Right, what did they want? They wanted young and female and... Oh, we already have the answer, by the way. Okay. Not such a speed run there, right? Young and female and single. Okay. Sorry for making you watch me stumble around like that. Okay, it's another one of these Venn diagram questions. All right. CBS, NBC, ABC. Oh, wait. What does HGTV have to do with it? Oh, how many did not watch any of the 4 channels? Okay. Fine. So, of those that watched HGTV, those are just completely separate. 18 for HGTV. Fine. 4 watched all 3. NBC, ABC, an additional 1 to total 5. CBS and ABC, that's 6, so 2 more than these 4. CBS and NBC, 7, that's 3 more than these 4. 34 watched CBS, we've got 9. 34 minus 9 is 25. NBC, 1 plus 4 plus 3 is 8, so you have 7 here. ABC, 10. 1 plus 2 plus 4 is 7, you need a 3 here. All together now, 25 plus 10 is 35. 1, 2, 3, 4 is another 10. That's 45 plus 18, 63. 100 total, minus the 63 we've already accounted for. Company prices hurricane insurance according to the following assumptions. In any calendar year, there can be at most 1 hurricane. Probability of a hurricane is 0.5. Number of hurricanes in any calendar year is independent. Using the company's assumption, calculate the probability that there are fewer than 3 hurricanes in a 20-year period. Okay, you know how I said you're not going to have a textbook case? This is a textbook. Okay, so this would be like one of the easiest ones. This, hopefully you recognize as a perfect binomial. For 0, you have 95% chance of no hurricane across all 20 years, 0.95 to the 20th. It's going to get you 0.358. For 1, you have 0.95 to the 19th times 0.05 for the one time a hurricane happens, times the 20 positions that the hurricane, or 20 years that the hurricane can happen. 0.377. It said fewer than 3, so that means only 0, 1, or 2. Often they won't make you do more than 3 of these. And so it's looking like it's going to be choice E just based on what we already have. But, yeah, 0.95 to the 18th times 0.05 squared times, for 20 choose 2. That's going to be 20 times 19 over 2. That's going to be 190. 0.188. Add them up. 8, 8, and 7. That's going to be a 3. Carry a 2. 2 and 8 is a 10. 5 and 7 is a 12. Carry a 2. Carry a 2. 2, 5, 8, 9. 0.92, yeah, 0.923. Okay, yeah, it was choice E like we thought it was going to be. Studies being conducted in which the health of 2 independent groups of 10 policyholders is being monitored over a 1-year period of time. Individual participants and sort of drop out before the end of the study with probably 0.2 independent of the other participants. What is the probability that at least 9 participants complete the study in one of the 2 groups, but not in both groups? Okay, so you have to realize that each group you're dealing with a binomial, right? So so you've got an 80% chance of staying in, right? Probability that all 10 in a given group stay in, right? It's, yeah, 2 groups of 10, yeah. So 0.8 to the power of 10 is going to be, for 10 staying in, 0.107. For 9 staying in, 0.8 to the 9th times 0.2 times 10 for which people can drop out, 0.268. All told, probability of at least 9 in one group, it's going to be 0.375. And then the probability of its being in one of the two groups, of having this in one of the two groups, but not both. So that would either mean 0.375 are in work for this group, but the 0.625, right, the remainder is not. Or the other way around, right? So you do 0.375 times 0.625 times 2 to get 0.469, choice E. Right? Which is essentially you now have the yes/no question, are at least 9 in there, right? So now it's like that's a Bernoulli trial, and you have the two groups, 2 Bernoulli trials, binomial of size 2, and you need exactly 1. Right? Anyway, an insurance agent meets with 12 potential customers independently, each of whom is equally likely to purchase an insurance product. 6 are interested only in auto, 4 are interested only in homeowners, 2 are interested only in life. Okay. The agent makes 6 sales. Calculate the probability that 2 are for auto, 2 are for homeowners, and 2 are for life. Okay, so this appears to be a trinomial distribution, I think. Yeah. So essentially, you're selecting 6 sales here, right? Yeah, wait a minute. How do we think about this again? If we ask first, what is the probability that exactly 2 of them are for auto insurance? Okay, yeah, so it's a modified hypergeometric. Yuck. Full disclosure, I do not particularly like the hypergeometric distribution. But yeah, okay. So, if you're saying 12 people, 6 sales, probability that 2 of them are... Well, you know what? Let's first say probability of both of them going for the life insurance. That's probably going to be easier to work with, right? So that means the first one needs, the first one, the first life insurance candidate goes for, it's 1 of the 6, that's 1 out of 2, times the second life insurance candidate, right? That's now 5 more sales out of a possible 11. Okay. Now if we move on to the homeowners insurance, right? So now, what's the probability that the first 4 homeowners that you choose are interested, right? Once you've gotten these 2 out, or actually, do we do a normal hypergeometric? Let's just stick to regular probability multiplication, right? Yeah. So this is life for the homeowner block. If we said probability of its being the first 4, right? So this first guy that you look at, okay, he'd be 4 out of the 10 who remain. Then 3 out of the 9. Then 2 out of 8. And 1 out of 7. Are we... Sorry. We're only doing 2 of them. What am I doing? First successful homeowner sale. Yes, 4 out of 10 times 3 out of 9. And then the remaining 4 homeowner sales would have to be failures, essentially. So you would say 6 out of 8, 5 out of 7, 4 out of 6, 3 out of 5, right? For your failures. I'm being an idiot here. That's... Sorry. There only are 4 homeowners interested people. Okay. Sorry about that. Okay. Life insurance. 2 people. They both have to say yes. Homeowners. 4 people. 2 have to say yes. 2 have to say no. And one other thing I forgot. Times 4 choose 2. That's 6. Okay. Now, once you have that, and you know that you're making the 6 sales, right? This is all based on the assumption of making the 6 sales. The remaining 2 have to be for auto insurance. If we start trying to multiply these out, do we get any nice cancellations? Not that I'm really seeing. Okay, fine. Numerator. 5 times 4 is 20. 5 times 6 is 30. 20 times 30 is 600. Times 18. 10800. Denominator. Okay, if I just say 10800 divided by, in parentheses, 2 times 11 times 10 times 9 times 8 times 7. And I'm getting 0.974. Choice D. Sanity check. Does that make sense? Probability of both life insurance people being interested is a little less than 1 in 4. Probability of both homeowners insurance people being interested. Rough estimate here. Around a little more than 1 in 3-ish at that point. Yeah, it's believable. Yeah. Okay. Store has 80 modems in its inventory, 30 coming from source A, the remainder coming from... This looks like a Bayes theorem question. Without replacement. Okay. 80 modems in inventory, 30 coming from source A, remaining coming from source B. Of the modems from source A, 20% are defective. Of the modems from source B, 8% are defective. Okay. Probability that exactly 2 out of a sample of 5 modems selected without replacement are defective. This is another hypergeometric distribution. It's a little bit it's a little funny about how you do it. What you have to realize is that 80 modems in its inventory. How many total defective? 30 from source A, of which 1/5 are defective. So 6 defective there. 50 from source B, right? That's the remainder. 8% of 50 is 4. So you have 10 defectives. So you're selecting 5 out of 80. And you would have to say you're selecting 2 of the defective ones, and you're selecting 3 of the non-defective ones. Okay. 10 choose 2 is 45. 72 choose 3, I don't know off the top of my head. Is that right? Is that times 54,740? Yeah. And then 80 choose 5, I don't know off the top of my head. 80 times 79 times 78 times 77 times 76 divided by 120. $24,040,016. Okay. And I'm getting a probability of 0.102. All right, in a group of 25 factory workers, 20 are low risk and 5 are high risk. Okay, 2 of the 25 workers are randomly selected without replacement. Calculate the probability that exactly 1 is low risk. Oh, this feels remarkably easy. Right? Yeah. Probability that the first person is low risk is 0.8. Probability that the second person is high risk is 5 out of 24. And there are 2 ways that can happen. 5 times 2 is 10, times 0.8 is 8. 8 over 24 is a third. Okay, losses covered by a flood insurance policy are uniformly distributed over the interval from 0 to 2. The insurer pays the amount of the loss in excess of a deductible D. Probability that the insurance pays at least 1.2 on a random loss is 0.3. Calculate the probability that the insurer pays at least 144 on a random loss. Okay. The insurer only pays in excess of the deductible. Fine. So I'm just going to sketch this out, right? You've got 0 to 2. $1.2 is here. Right. Oh, that the insurer pays at least. Sorry. No. Okay. Okay. The 70th quantile, right? This probability of 30 of exceeding that, right? 70th quantile is going to be at 1.4, right? There's a 30% chance of exceeding that 1.4, which means if the insurer is paying 1.2, that means the deductible must be 0.2. For the insurer to pay at least 1.44, we're looking at a 1.64. This would mean probability of paying more than that. 1.64 to 2 is a gap of 0.36 over a full width of 2 equals 0.18. Group insurance policy covers medical claims of the employees of a small company. Value V of the claims made in 1 year is described as V equals 100,000 times Y, where Y is a random variable with this density function, where K is a constant. What is the conditional probability that V exceeds 40,000, given that V exceeds 10,000? Okay. Okay, 100,000 times y. Got it. So essentially, we're looking at probability that y is greater than 0.4 divided by probability y is greater than 0.1. Normally, for conditional probabilities, you don't just divide a simple probability by another. You would have an intersection. But y greater than 0.4 intersect y greater than 0.1 is just y greater than 0.4. And that's a technique that's going to show up a lot more if you go on to take the life contingencies or whatever they're calling it now, the LTAM. Yeah. Okay. So for this one, we're looking at integral from 0.4 to 1 of k times 1 minus y to the 4th dy, which is going to be, you can do a u substitution, u equals 1 minus y. Might as well do that. You're going to get negative out of it. To do that, we can just flip the bounds. What don't I like about this? Why does it look like I'm getting a negative here? Hold on. U equals 1 minus y. Oh, because that lower bound should be a 0. Blech. 0.6 to 0. So that is going to equal k times 0.6 to the 5th over 5. In our denominator, if we've got integral from 0.1 to 1, k1 minus y to the 4th dy, same u substitution. Upper bound is now 0.9, lower bound is 0. It's going to be ku to the 5th over 5. So k 0.9 to the 5th over 5. Notice that because our lower bounds are 0, we can kind of just ignore them. We divide them. K over k cancels out. Over 5 over 5 cancels out. What we want is 0.6 over 0.9 to the 5. Notice that 0.6 over 0.9 is 2/3. 2/3 to the 5 is going to equal 32 over 243. 32 divided by 243 is going to get you 0.13. Loss due to a fire in a commercial building is modeled by a random variable x with this density function. So it's triangular down. Given that a fire loss exceeds 8, what's the probability that it exceeds 16? Okay. No integration necessary. The probability density function looks like this. This is a 20 here. We've got an 8 here. We've got a 16 here. This distance here to here is a 4. This distance here to here is a 12. We're saying what's the area of this triangle divided by the area of this triangle. We have two similar triangles with an edge length ratio of 3 to 1 or 1 to 3. Area is proportional to the square of the edge length. Square of 3 to 1 is 9 to 1, or 1 to 9 because we're doing the other way around. Okay. In modeling the number of claims filed by an individual under an automobile policy during a 3-year period, an actuary makes the simplifying assumption that for all integers n greater than 0, Pn plus 1 equals 0.2 Pn, where Pn represents policyholder file. Probability that the policyholder files exactly n claims during that period. What is the probability that the policyholder files more than one claim during the period? Okay, notice we have ourselves a good old-fashioned geometric distribution here. You have to kind of realize. So here the trick is you're kind of using it two ways, right? You've got a geometric distribution. You have to figure out what your starting value is, right? If you're decaying by 0.2, yeah. So each one's like 80%, or yeah, 4/5 of the previous one. I think that means your starting value has to be 0.2, right? Yeah, because if you started on a 1 geometric series formula, 1 plus 4/5 plus 4/5, you do b over b minus a. You get a 5, so you have to scale down. Okay, so you've got a probability of... wait a minute. Sorry, 1/5. 1/5, not 4/5. Blah, 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 blah. The point is, if you were to start with a 1 plus 1/5 plus 1/5 squared, right? You do, when you've got a simple fraction like this, either 1 over 1 minus r or b over b minus a, where your original fraction is a over b, right? So you would get 5 over 6. Sorry, you would get 5. You get 5 over 4, which means you have a probability 0.8 of filing exactly 0 policies. You multiply by 0.2, you get 0.16 for filing exactly 1 policy. You want probability of more than 1. So this is 1 or less, that's 0.96. You want 1 minus that. Okay. Under an insurance policy, a maximum of 5 claims may be filed per year by a policyholder. Let Pn be the probability that a policyholder files n claims during a year. N is 0 to 5. Actuary makes the following observations. Pn is greater than P. Okay, so it's a decreasing thing, right? The difference is the same for n equals 0, 1, 2, 3, 4, and 5. 40% file fewer than 2. Okay, here we go. This is where we say, right, suppose that everything were just even, right, across the 6, so that would be a 1 over 6. And then whatever amount is kind of getting added in, right, you've got amounts getting added here and subtracted here. What does it want? It wants probability of filing more than 3 claims. So we know the answer's got to be some amount less than a third. Okay, fine. And we know that 40% file here. Yeah, so if we were to add in some percentage off center, right? We'd give, so to go from this imaginary center would be 2.5, right? So if we have 1x from 2.5 to 2, we double that difference, 3x, right? 5x. Okay, so what we have is that 1/3, that's these 2 1/6 if it were even, plus 8x equals 0.4. That could be 2/5. Common denominator 15. 5/15, 6/15. 8x equals 1/15. X equals 1 over 120. What we're looking for here would be more than 3, so that's 4 or 5. That would be 1/3. We have a minus x here, minus 3x, minus 5x. So we would have 1/3 minus 8x. Well, we have 8x equals 1/15 here, so we have 1/3 minus 1/15. 1/3 is 5/15, so it's going to equal 4/15. Which is 0.27. Working lifetime in years of a particular model of bread maker is normally distributed with mean 10, variance 4. Calculate the 12th percentile of the working lifetime in years. For this, you typically be given a normal distribution table, I think. Or at least back when they gave you an actual table rather than a built-in calculator. Okay, fine. This is actually surprisingly textbook. We've got a standard normal table. To get, okay, these are right tail probabilities. Fine. 12th percentile would be like 1.175 as a z-score. In this case, it's actually negative 1.175 because you're at the low end. Your standard deviation, your variance is a 4, so your standard deviation is a 2. So 10 minus 2 times this. Equals 7.65. Insurers' medical reimbursements have density function f of x, where f of x is proportional to this. Calculate the mode of medical reimbursements. Modes where it's got maximum likelihood. That's going to, so you're essentially looking for a critical point. Derivative with respect to x of xe to the negative x squared is going to be a so standard product rule. Derivative of the first times the second plus first times derivative of the second. Well, okay, so there's a minus in there, right? Derivative of this is minus 2x, so minus 2x squared right? What we get, if we factor this out, e to the negative x squared times 1 minus 2x squared. Sanity checking here, if we plug in, if we plug in x equals 0 to the original, we get a probability of 0, so that's got to be a minimum. If we plug in x equals 1, notice we get a negative derivative. We get some quantity minus double that quantity. So it's on its way down. So the mode will be somewhere between those two. At a mode, right, we're looking for where derivative is 0. E to stuff is never 0. 1 minus 2x squared equals 0. X squared equals a half. It's going to be 0.71. Root 2 over 2. And insurance policy reimburses dental expenses up to a maximum benefit of 250. The probability density function for x is this thing, where c is some constant. Calculate the median benefit for this policy. Okay. Okay. Dental. Okay, the expense is X. The benefit is either X or 250, whichever is lower. Okay. Using the good old-fashioned 69 rule, right, to go from a median, to relate median to time constant, right, because they're specifically asking for median. We'd say median equals 0.69 times the decay constant, or essentially times 1 over the decay constant. So it's going to be 250, not because 250 is the maximum benefit, but because it's 1 over 0.004. I'm getting 172.5. Yeah, it's going to be 173, right? The 0.69 is a slight. It should be like 0.693. It's natural log of 2, but how many digits do you really want to remember natural log of 2 to off the top of your head? Heck, you could have just plugged it in. What was that? But yeah. Okay. Let x be a continuous random variable with density function p minus 1 over x to the p if x is greater than 1, 0 otherwise. Calculate the value of p such that e of x equals 2. Is this a shape I just flat out recognize? I don't think so. Okay. All right. If we're just going to integrate from 1 to infinity of, now it's going to be density times density times your times x, right? So p minus 1 over x to the p minus 1. Raise the power by, or you can just write this. X to the 1 minus p. Raise the power by 1 and divide by the new power. Right. Let's write x to the 2 minus p times p minus 1 over 2 minus p from 1 to infinity must equal a 2. Right? Notice that when you plug in, hold on. Well, okay, so for this value not to just go infinite, I think p must be at least 2. Yeah, p must be at least 2. Well, yeah, the answer choices would do that. Right? Yeah, so p must be at least 2. So you plug in x equals infinity. This is just going to 0. Right? You plug in x equals 1. 1 to whatever is just a 1. So what we have is this negative of p minus 1 over 2 minus p equals a 2. Negative p plus 1 equals 4 minus 2p. Add 2p to both sides. Subtract 1. Yeah, I'm getting p equals 3. Just to sanity check this, if I were to integrate from 1 to infinity, 2 over, at p minus, 2 over x squared dx, then I would get 2x to the negative 1 from 1 to infinity. Sorry, negative 2x to, well, okay, so get rid of the negative and just swap the 1 and the infinity, right? 2 minus 0, yes, does equal 2. It's choice C. It's answer 3. Okay, there we go. Let N1 and N2 represent the numbers of claims submitted to a life insurance company in April and May, respectively. The joint probability function of N1 and N2 is this thing. Calculate the expected number of claims that will be submitted to the company in May if exactly 2 were submitted in April. So we're assuming N1 equals 2, and you want the expectation, the conditional expectation of what is submitted in May. Okay. So we're saying probability density of 2, comma, N2, right, because we said N1 equals 2, is going to equal 3/4 times 1/4 to the 1 is going to be 3/16 times e to the negative 2 times, this is going to be 1 minus e to the negative 2 to the n2 minus 1. Okay. This looks like a geometric distribution. Right? Am I reading that right? Oh, yeah, and that's okay. Yes. Yeah. Hold on. Right, because this is just a scaling constant. You've got... No, that I'm not meeting with that student anymore. On 1. Without this, you've got a decay constant of 1 minus e to the negative 2. This feels like a geometric distribution. Let me make sure I'm... Why are all the e's coming up positive, though? That bugs me a little bit. If n2 equals a 1... Oh, is that going to matter? Hold on. If n2 equals a 1, you've got some joint probability x. Let's call this a k. If n2 equals a 2, you've got kx. If n2 equals a 3, you've got a k squared x. If n2 equals a 4, you've got k cubed x, etc., etc., etc. Okay. Where x is just some arbitrary probability. Since we're going to be taking first moments divided by total probability, we can actually just factor out the x. We can say it's going to be 1 k squared, k cubed, etc., etc., etc. So if we wanted, this is for a 1. This is for a 1, a 2, a 3, a 4. Our k equals 1 minus e squared. So if we wanted, numerator is going to be a first moment. 1 plus 2k plus 3k squared plus 4k cubed, etc., etc., etc. Our denominator is just going to be 1 plus k squared plus k cubed. This is a standard geometric, right? Well, 1 over 1 minus k, I think. This up here is gonna be and I guess 1 minus, okay, wait a minute. 1 minus k is going to be e to the negative 2. So our so this gets you something involving an e squared. Hold on, you know what? I'm just blanking on this. Let's make absolutely certain of this. If I say 1 plus k squared plus k cubed, etc., 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 equals our denominator. Multiply by k plus k squared plus k cubed, etc., equals k times our denominator. Subtract. 1 equals 1 minus k d equals 1 over 1. Yeah, okay. I'm remembering my geometric series formula correctly, and I'm applying it correctly. Numerator, you have to do the trick twice. 1 plus 2k plus 3k squared, etc., 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 equals numerator. Multiply by k. Actually, let's do one more. 4k cubed. 5k to the 4th, actually, just to really make sure the pattern shows up, because we're doing this twice. K, I'm multiplying by k. Subtract. Do it all again. Subtract. 1 minus k times 1. Okay, so that's going to be 1 minus k squared times n. N equals 1 over 1 minus k squared. So what we have here, numerator, 1 over 1 minus k squared. Denominator, 1 over 1 minus k. Multiply numerator and denominator by 1 minus k squared. Multiply numerator and denominator by just by 1 minus k. Right, because then your denominator just goes to 1. Okay, so that's our fraction. 1 over 1 minus e to the negative 2. Yeah, it's going to be 1 over e to the negative 2 is going to equal e squared. Okay. I double and triple checked myself there. Yeah, you probably should have. If you're watching this, my apologies. You were entitled to see me do that faster instead of stumbling over myself there. Times failure of a component in an electronic device has an exponential distribution with a median of 4 hours. 69 rule again. Calculate the probability that the component will work without failing for at least 5 hours. Well, we know it's got to be less than half, right? Exponential distribution. We said 4 equals 0.69 times the mean, right? Relating mean to median. Four divided by 0.69 is going to be 5.80. So this will have a probability density function of of some alpha times e to the negative 1 over 5.80x. A survival function, right? That's 1 minus probability density function of just regular e to the negative 1 over 5.80x. And you just plug in x equals 5. E to the negative 5 over 5.80. And I'm getting a 42% survival rate. Does that make sense? Half the time it lasts 4 hours. That means a quarter of the time it lasts 8 hours. If we were to linearly interpolate and approximate that way, you figure it loses like 8-ish% per. Yeah, okay. Yeah. Claim amounts at an insurance company are independent of one another. In 1 year, claim amounts are modeled by a normal random variable x with mean 100 and standard deviation 25. In year 2, y equals 1.04x plus 5. Okay. So the randomness in y is completely determined by the randomness in x. Calculate the probability that a random sample of 25 claims random sample of 25 average between 100 and 110. Okay. So if we're saying mean of y is between 100 and 110, y equals 1.04x plus 5. So you can subtract the 5 first. It's going to be between 95 over 1.04 and 105 over 1.04. 91.35 versus 100.97. It's normally distributed. Standard deviation is 25. This is a z-score of 0.039. This is a z-score negative 0.346. Okay, 0.039 to 0.346, or to negative 0.346. Double check our normal distribution table. Point 0.04. Okay, that would get you, well, on the positive side, so it would be 1 minus this, right? So 0.5160 minus 0.346. Okay, well, we're talking about like 0.35-ish. Oh my goodness, wait a minute, what did I mess up here? Okay, wait. I forgot that we're taking a random sample of 25. My apologies. So when we said this 100.97 versus 91.35, that I'm not meeting with that student anymore. Why is it getting me notifications? Your standard deviation for one person was 25. Your standard deviation for a group of 25 is going to be divided by 5, so it's 5. Okay. So here we have 0.97 divided by 5. .194. Standard deviation here, or yeah, so 91.35 minus 100. You divide that by 5. Negative 0.183. Okay, fine. .194 is negative 0.193. So 0.194. And that's the positive version. So you're looking at 0. Wait, that doesn't make sense. Oh, hold on. 0.5753 versus, I think I messed this up here. 91.35 minus 100. Yeah, you divide that by 5. Yeah, we should be looking at minus 1.73. I just flat out messed that up. 0.0418. And yeah, you get like 53%. Unless Is it gonna round to 54% because I stopped at 0.9? How much extra gets added in here? You add in an extra like 0.4%. Okay, I think it rounds up to here. But if I end up being off by that, because I'm, okay, I'm not sure what sort of normal distribution calculator you're allowed these days, but okay, yeah, fine. Proportion X of yearly dental claims that exceed 200 is a random variable with this probability density function. And you want the variance of X over 1 minus X. Okay, yeah. Oh, hold on a minute. Okay, you have, sorry. Yeah. Is there some sort of trick to this? No, I think you just want to get, okay, so. Fine, yeah. I think all you do here is your mean of the square minus square of the mean. Right. So expectation of X over 1 minus X is going to be integral from 0 to 1 of you multiply this whole thing by X over 1 minus X. So 60 X to the 4th 1 minus X. You could do U substitution, or you could just, FOIL it all out. Integral from 0 to 1. 60x to the 4th minus 60x to the 5th. So 60 over 5 minus 60 over 6. 12 minus 10 equals a 2. Expectation of X over 1 minus X squared, right? This is mean of the square. Integral from 0 to 1. 60x to the 5th. With nothing else after that. Equals a 10. Right? Variance is mean of the square minus square of the mean. 10 minus 2 squared is going to be 6. Okay, that problem was not as scary as I thought it was going to be. A student takes a multiple choice test with 40 questions. We're thinking something binomial. The probability that the student answers the question correctly is 0.5, independent of all of the questions. Probability that the student answers more than n questions correctly is greater than 0.1. Probability that the student answers more than n plus 1 question correctly is less than 0.1. Calculate n using a normal approximation with the continuity correction. Okay. Fine. 40 questions. We'll say mean equals 20. Standard deviation equals square root of 40 times a half times another half, so square root of 10. Critical z-score. Let me just pull up. For this to go from above to below, you're looking at like 1.28-ish. Okay. So that critical point right there, if you were to say 20 plus 1.28 times square root of 10, (24.04). So we'd say that the 10th percentile, or that 90th percentile is somewhere between 23 and a half and 24 over half, 24 and a half, right? So it's somewhere in that bank of 24s. Is where that 90th percentile is going to be. So we would say fewer than 90%, more than 10%. More than 10% would get 24 or more correct. Did I mess something up here? We're saying more than, get 24 or more correct. Nope, we're fine. Yeah. Yes. More than 10% would get 24 or more correct. Fewer than 10% would get more than 24 correct. That agrees with n plus 1 being 24 or n being 23. There we go. Driver and passenger are in a car accident. Each of them independently has a probability 0.3 of being hospitalized. When a hospitalization occurs, the loss is uniformly distributed between 0 and 1. When 2 hospitalizations occur. Finally, a triangle question. Calculate the expected number of people in the car who are hospitalized given that the total loss... Oh, maybe it's not... Given that the total loss... Hold on. Due to hospitalizations is less than 1. Okay, we'll see. We'll see if this is a good triangle question. Zero, 1, 0, 1, right, because the loss is uniformly distributed there. Total loss due to hospitalization is less than 1. Yeah, I mean, you can sort of see a triangle, right? You're seeing this. Okay, areas. 70% chance that any given person is not hospitalized, so you've got, for 0 hospitalizations, you've got 49%. For 1 hospitalization, you've got a 21 here, 3 times 7, a 20, or it's a 21 here. That's a 42. For 2 hospitalizations, you would have a 9% for just everything here, but you only have half of that, right? Because you only have half of that area. 4.5. 0 of this, 1 of this, 2 of that. 51 divided by 491, 95.5 is the total. .534. Number of severe storms that strike city J in a year follows a binomial distribution with n equals 5, p equals 0.6. Given that m severe storms strike city J in a year, the number of severe storms that strike city K is m with probability half, m plus 1 with probability a third, and m plus 2 with probability a sixth. Okay. Calculate the expected number of severe storms that strike city J in which 5 strike city K. Hold on. Which direction is this? Five storms strike K. Okay, and it's, yeah, okay, fine. So we have to think about 3 hit J, 5 hit K. We have to think about 4 hit J, 5 hit K, and we have to think about 5 hit J, 5 hit K. Because K is either equal to J, or 1 more than J, or 2 more than J. Okay. This one is going to be 5 choose 3, right? So 10 times 0.6 to the third times 0.4 squared. And then that's probability of 3 hitting J times another 1/6. That gets you 0.0576. Four hit J, 5 hit K. All right, that's going to be 5 times 0.6 to the fourth times 0.4 to the 1, right? Times a 1/3 chance of 1 more hitting K than J. .0864. 5 hit J, 5 hit K. That's just 0.6 to the fifth times 0.5. 0.0389. We can already see the answer is going to be some amount less than 4, not some amount more than 4, because there's a greater probability of seeing a 3 than a 5. Right? We'll do, 0.0536 times 3. Oops, what did I just do? And we can actually get rid of the .0's, right? We can just say 536 times 3 plus 864 times 4 plus 389 times 5. Numerator ends up being 7,009 divided by 536 plus 864 plus 389. $7,009 divided by 1,789 gets me a 3.9. In a large population of patients, 20% have early stage cancer, 10 have advanced stage cancer, 70% do not have cancer. 6 patients are randomly selected. Calculate the expected number of selected patients with advanced stage cancer given that at least one has early stage cancer. Okay. So immediately, right, seeing it, if you just had the 10% with the advanced stage cancer, right, so if you didn't have the rule about at least one has early stage cancer, right, the answer would be 0.6. And the fact that at least one specifically has early stage cancer. So you're ruling out all the cases where none of them have early stage cancer. So the answer is going to go down somewhat, right? Because if you don't have early stage cancer, there's a slight chance that you instead have advanced stage cancer. Okay, so the requirements of at least one having early stage would slightly decrease the probability, not slightly increase the probability. So it's either going to be choice A, B, or C. Right? Okay, fine. And so now what I would say here is that overall, the number that overall, right? If we didn't, so if we break this down into, if we didn't know that at least one had early stage cancer, the overall answer would be 0.6. If we break this down into no early stage and somebody having early stage, right? We know that if nobody has early stage, now we're not just looking at 10% out of 100%, we're looking at 10% out of 80%, right? So the probability of any given person having advanced stage cancer is no longer 1/10, it's 1/8. 6 times 1/8 is going to be 0.75. And the probability of none of our 6 having early stage cancer is going to be 0.8 to the 6th, or 0.262. Which means our remaining 0.738 are cases where at least one has early stage cancer. This will get us some probability x, which is exactly what we're trying to solve for. 0.262 times 0.75 plus 0.738 times x equals 0.6. Isolating for x, I'm getting 0.547. At a polling booth, ballots are cast by 10 voters, of whom 3 are Republicans, 2 are Democrats, and 5 are independents. A local journalist interviews 2 of those 3 voters chosen randomly. Calculate the expectation of the absolute value of the difference between the number of Republicans interviewed and the number of Democrats interviewed. Okay. 2 of these voters chosen randomly. All right. So I would say here is your difference will be 0 if you have RR, DD, II, right? Any of those pairings, right? Notice if you're choosing 2 out of 10, right, that is a total of 45 combinations. 2 Republicans, right, 2 out of those 3. That's 3 possibilities. 2 Democrats. Sorry, wait a minute. No, sorry. Blah, 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 blah. No, it's RD or II. That's what will get you a 0. Okay, out of 45 possibilities, to go for a Republican first and then a Democrat would be 6. Democrat first and then a Republican would be another 6, so that's a 12. Choosing 2 independents, 2 out of those 5. 5 choose 2 is a 10. So that's 22 out of 45. For a 1, that's going to either be an RI or a DI. For a Republican and an independent, or well, I guess you could say it's just independent than anybody who's not an independent, right? So that would be 5 times 5 if you do the independent first, or if the non-independent is first, also 5 times 5, right? Wait. Am I mixing and matching between ordered and unordered? Let's be careful about this. If this is just what we're choosing, hold on. Any two independents, any Republican and any Democrat. I think so. I never said who was first. One Republican, one Democrat. Sorry, that's a 6. That's going to make this a 16. Yeah. And then here, this is all 25, right? Any of the 5 partisans plus times any of the 5 independents. To get an absolute value of 2, you either need RR or DD. There's only one way to get DD. There are 3 ways to get RR. There we go. Yeah. And so the expectation of this absolute value, 16 times 0, 25 times 1, 4 times 2. You get 33 over 45. Common factor of 3. 11 over 15, choice D. Let's just sanity check that, actually. It's a little less than 1. Yeah, but you're more likely to get RD or II than RRDD, right? If we look back here, yeah, you've got a much lower chance of getting kind of rolling doubles, if you will, or rolling double partisans, yeah. All right. Number of hurricanes that will hit a certain house in the next years is Poisson distributed with mean 4. Each hurricane results in a loss that is exponentially distributed. With mean 1,000, the losses are mutually independent and independent of the number of hurricanes. Okay. Way back in 2011, when I took this was a style of question that I'm pretty sure I got wrong when I took this way back then. Yeah, this is law of total variance. Total variance of the loss is going to be variance explained by variance in number of hurricanes plus variance not explained by that number of hurricanes, right? So the explained variance is going to be 4 times variance of a single loss plus expectation. Right, so on average you'll get 4 Sorry, this isn't variance of a single loss. This is squared mean of a single loss, right? Because if you're saying, right. Yeah, this is squared mean of a single loss. This is saying my variance of the number that hit is a 4. Each one gets multiplied by 1,000, but because variance deals with the square of the quantity you're calculating, right? Yeah, you're scaling by, yeah. Here, you'll say another mean of 4 times individual variance, right? So each one has a variance of 1,000,000. So it should be 8 million. Hopefully I didn't mess that up again 14 years later. An actuary determines that the annual number of tornadoes in countries P and Q are jointly distributed by this tiny little table that has a button that says click to enlarge. So let's enlarge it. Oh, Yeah, there we go. Okay. Calculate the conditional variance of the annual number of tornadoes in County Q. I think I said countries rather than counties. Given that there are no tornadoes in County P. Okay. Fine. What is it? 12,652. Overall sum of these 12, 18, 25. So how do we want to do this? Yeah, let's convert these to conditional probabilities, right? Conditioned on there being 0 here, we have 0.48, 0.24, 0.2, 0.08. This is for numbers 0, 1, 2, and 3. Let's do mean of the square minus square of the mean. 48 nothings, 24 plus an additional, we double that for 40, is going to be 64, right? 24 plus 40 is 64, plus another 0.24, right? So 0.88 equals mu. For mean of the square, 0, 24, 4 times 0.2 is 80, so that's going to be 1.04. 9 times 0.08 is going to be 0.72. 1.76 equals e of x squared. 1.76 minus 0.88 squared. I'm getting 0.9856, or like a 0.99. Did it want variance or standard deviation? Variance. Okay, so I don't need to take a square root at the end. All right. Insurance company insures a good driver and a bad driver on the same policy. The table gives the probability of a given number of claims in the next 10 years. I don't think that's per year. Number of claims occurring for the two drivers are independent. Calculate the mode of the distribution of total number of claims occurring on this policy in the next 10 years. Okay. So I would just calculate directly until stuff starts to go down. Probability of a 0, you need to roll double 0. That's 0.1. Probability of a 1, it's either 1 for the good driver and none for the bad driver, which is going to be 0.06, or none for the good driver. Okay, so 6 plus 15, 0.21. Okay, so, 2. That's either going to be none for the good and 2 for the bad. That's going to be a 20. 1 and 1, that's going to be a 9. Right, so 29. 0 and 2, that's going to get you an extra 4, so that's going to be 0.33. 3 crashes. Notice that you can't get the 3 here, so it's either going to be none here and 3 here is going to be a 5. 1 here and 2 here is going to be a 12, subtotal 17. 2 here and 1 here is going to be a 6, subtotal 23. It's looking like 2 is our mode. But we might as well also check out, right, the maximum. You can't even get a 6, right? We might as well go up to 5 because we've got a little bit of time. Now, the none is irrelevant. 1 for the good and 3 for the bad is going to be 3, 2 for the good, and wait, sorry, 1 and 3. Yeah, 2 for the good and 2 for the bad. It's going to be an 8, so that's going to be an 11. By the way, 10, 31, 10, 31, 64, 87, 98. Yeah, because then for a 5, the only way to do that is 2, and that's going to be an 0.02. There we go. Okay. And finally, charity receives 2025 contributions. Contributions are assumed to be independent, identically distributed. Mean 3125. Standard deviation 250. Calculate the approximate 90th percentile for the distribution of the total contributions received. Standard normal stuff. Yeah, we would say 3125 times 2025. I don't know that off the top of my head. Six, 328, 125. Standard deviation is going to be the standard deviation for a single one, 250, times the square root of the number of contributions you have. Square root of 2025, I believe, is 45. Right, so 250 times 45. Yeah. 11250. For 90th percentile, we want mean plus 1.28 standard deviation. I'm remembering that 1.28 because we looked it up earlier, but plus 6328125. And I'm getting choice C, 6,343,000. Okay. Apparently I messed something up somewhere. Let's see if it shows me what I messed up. Nothing wrong there, nothing wrong there, nothing wrong there, nothing wrong there. It was that one with the round off error. Okay. Yeah, I'm not. Yeah. Given. Yeah. Okay. Okay. Fine. Yes. Unless, did I mess something up somewhere? Oh, they are. Okay, yeah, that's yeah. Okay, maybe I should have said that. Yeah, that the y is randomly distributed with that. I'm wondering if the round off just happens a little bit differently. Because I did get something between those two. Because if you remember, I calculated backwards that my calculation involved dividing by 1.04. Yeah. Yeah, okay. But yeah. So hopefully you found this useful. If you have any questions about what sort of stuff I did, feel free to ask in the comments below. And until next time, this is Dr. Nighttime wishing you a good night.